I love these Calvin and Hobbes Snowman comics. So you don't like my Snowman House of Horrors, do you? He's talking to his mom. And it's cool. These have inspired people to make the real versions. So like here's someone who did this comic in real life. So they got the little guy sledding through another one, the multiple nose, carrot nose guy, and then the one who's sinking into the snow and the tree growing up. And I guess that's the one with the head off over there. It's kind of hard to see, but here's another one. I like this one. Snow sharks. That guy's a goner. So the snowman's trying to swim away from snow sharks. And then this one, I don't think schools assign enough homework because his son's making all this snow monster eating snowmen. And then here's someone created that one too. Pretty awesome, huh? The effort. So today we will have announcements and then the final exam review. And yeah, we don't get snow in the winter. We get fog. Fog feels like Christmas season to me. So if you were not able to complete all parts of the chromatography lab in person, do the parts you did not get to do in person on the chromatography online version. So you'll find that here and in the step-by-step. And then the distillation and GCMS lab, that's all online. Next semester, we'll do distillations and use the GCMS in person. And you can turn all of these, both of these in by Saturday, this Saturday, and I won't count it. I won't count it late. So, but be strategic about your study time. Study for the final before you focus on these. And then final exam details again, 3 hours, but you can have longer if you like. You can come in early. So today, if you want to start early, come in at 1 p.m. instead of the normal 2 p.m. And then every other lab section, come in an hour early too. And you'll just place your cell phones at the front. Don't make a lot of noise. No notes allowed. The exam, again, is always cumulative. And it'll be over chapter 7 outcomes, mass spec material, chapter 8, only a little bit of chapter 8, which I outline here. So we went through all this already. This is the same as before. Review, maybe this is a little different. No, I guess I said this last time, huh? The stereochem RNS and review your pKa values. That's the pKa values. Okay, alcohol synthesis, yep. And this is some of the older stuff I'd mentioned, can go on there. No chapter 8 homework, and that's about it. Any questions about that outline? Okay, so let's get into some practice. So getting ready for this exam. I can do whatever you'd like. I don't have enough time to do an example of everything we've done this semester in this review, but you can help direct me if you're like, oh, you know what, it'd be great if you did this. But if you don't have any suggestions, I'll just go with what I think sounds good too. Okay, I got a request for alcohols. I could do that. Mclafferty, yeah, we could do that too. Okay, let me do the alcohols first. So the alcohol synthesis, it's basically chapter 7. And let's see here. I want you to be able to make methyl alcohols. Methyl alcohols, I'll try them all. Primary alcohols. Secondary. And tertiary. And understand what the reactions you're using to make them. And I want you to make those from pure alkanes. So let's do these. I'll just do these quick and then I'll do the other ones too. So for the methyl alcohol, I start with methane. And then I add bromine and light. For all the alkanes, you always add just bromine and light to start. H nu, energy of a photon. So you make bromomethane. And then since it's a methyl electrophile, it can only do SN2. Can't do SN1 or E1 because it can't make a carbocation. It can't do E2 or E1. It's only one carbon. So it can do only do SN2. So I can add a strong base like sodium hydroxide. No worries about E2. And try to speed up this E2. I can add like a polar aprotic solvent like DMSO. And there we go. Our major product will be methanol. For primary alcohol, I could use like ethane here. And again, bromination and light. And then this one's primary unhindered. So it can do, can only do SN2 and E2. It cannot do SN1 or E1 because SN1 has a carbocation, E1 has a carbocation, and you can't make primary carbocations. They're just too high in energy. So we can do SN2, and if we use sodium hydroxide, it's right at the limit, but it will make your, it will make the SN2 product as major. And I'll go ahead and add another polar aprotic, dimethylformamide, DMF. And the SN2 will be major, which we'd want for this. There will be a minor amount of E2, but that's okay. We can purify that away, the alkene. All right, now for a secondary electrophile, I can add propane, but actually it doesn't have to just be propane. It can be a lot of things. It can be butane, cyclopropane, cyclohexane. Let's do a cyclopropane, why not? Switch it up a little bit. So if we brominate this one, that kind of got ugly. Get the monobromo product here. It's only one regioisomer for this, no stereochem. And now we have to be careful. If I add sodium hydroxide, that would be bad. Add sodium hydroxide is too strong a base for secondary, so this would be E2 major. But if I add a weak base like water that can wait around for a carbocation, keep it cool, SN1 will be favored. There will be some E1 as well. That's the minor product. Plus, you know, the hydronium and the bromide. Okay, and now tertiary. I'll do that on the next. Oh, I'll just do it all on one page. Let's do this. Oh, come on. Yeah, no, I'm going to the next page. So tertiary alcohol, I could start with anything with the tertiary carbon. This will work. If I brominate this, the major product will be the tertiary bromide because it reacts 1,700 times faster there than primary and faster than secondary too. And now again, it's tertiary, so there's no SN2 for this one.
Mark.
Yeah. Oh, I didn't switch.
We can't see the screen.
Thank you so much. So this one is no SN2. So I started off with a different than just, I could have just had, you know, these carbons, but I can do this too, make it more interesting. So that'll be my major product with the bromine there. Can't do SN2, so it has to do SN1. Keep it cool. And your major product will be that one. You'll get E1 as well, but SN1 will be major because we cooled it. All right, let me go down the list here. I had a request for Mclafferty rearrangement. Let's do one. We'll do an interesting one. Let's see. So we start with our molecule. Before it enters the mass spec, it gets hit with an electron beam, and that gives it charge. It can knock off a pi bonding electron or a sigma bonding electron or a lone pair, but it knocks off the lone pair most often. And this would be an easy one for me to miscount, huh? Let me count this. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I added extra. Good thing I counted. Okay, and then for the Mclafferty, I have to count around from the oxygen to a hydrogen, 6 atoms. So if I go this way to the left, 1, 2, 3, 4, 5, not far enough. So I'm gonna have to go the other way. Let me count it this way. 1, 2, 3, 4, 5. I'm gonna have to have a hydrogen off of 5 that reacts. That'll be my 6 atoms, right? So this whole thing can be drawn in its reactive conformation. 1, 2, 3, 4, 5. That's my hydrogen there. Let me use my green numbers, make sure I got those right. Okay, then after carbon, off of carbon 5, I got a bunch of other carbons, right? I got all this stuff. Should be, let me count again, 9 across, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, 1, 2, 3, 4, 5, 6, 7, 8, 9. Looking good. It's all set up for my mechanism. So imagine this oxygen's a hinge. The pi bond swings out to deprotonate that hydrogen. And then this carbon 5 has a hinge on it. So then this bond can swing down. And then the carbon 3 has a hinge. So this bond will swing over there. So when I look at this, I see I'm going to get a new single bond between the oxygen and the hydrogen. I'm going to lose the hydrogen carbon here, but I'm going to gain a pi bond there between 5 and 4. And then I'm also going to gain a pi bond between 3 and 4 there, huh? Okay, so let me try to draw that product. I'll show you a trick that you might like if you're working this out on like a paper with a pencil that you can erase, or a pen. Now you can erase a lot of pens. One way you can help yourself draw the products is you can just draw the reactants exactly the same initially, and then like just erase things. I'll show you what I mean. So see, right now I'm drawing the exact same thing, the reactant, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. And then what I do is I just like add the bonds I need. So I'm going to add this bond right here. That's the new bond, and erase this one here because I know that's going to swing down to there. And then I'll erase this one because I know that one's going to swing over to here. Oh, and I should have already erased that one because it's swinging up to get that hydrogen. So there we go. There's my product. And then my which fragment will show up on the mass spectrometer? The positive charge one. So what's its formula? C1, 2, 3, 4. C4H2, 3, 4, 5, 6, 7, 8. Oxygen. Let me double check that. 1, 2, 3, 4, 5, 6, 7, 8. Yep. 1, 2, 3, 4. Oxygen. Yeah. So what is this way? 44, 48, and 8. That's 56 and 16 to 72. So I'd expect that one to show up at 72 mass to charge ratio. Okay, I hope that helps with your Ashley with Mclafferty. So Santos, the kinetics versus thermodynamics, we haven't really focused on that yet. We're going to focus on that more next semester. So I'll wait on that one. And then Ryan Jackson, can you do number 4 from exam 3, the bromination one? Let me look at that one. 4 from exam 3. I'll do this one quickly, Ryan. I do have the answer key, of course, for this, right? Let me just get the main things across here real quick, though. My iPad's catching up. Let's go iPad. Oh wait, I was on the wrong panel. I was on panel 4 and this is number 4. I was confused. All right, let me just draw out the products really quick for this one. So you got a bunch of regioisomers, 1, 2, 3, 4, right? And I'm just going to add them with their stereochem too. So the first one here, no stereochem. And then the next one across the top, it's going to have 2 stereoisomers. Beep, 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 beep. Because it makes enantiomers there. And then the one on the far right, no stereochem, just done easy. And how much of these are we going to make? For this one, we're going to make, it's got 3 hydrogens times 1 reactivity. So it's going to be 3 over the total of 3 plus 2 times 80. Plus 3 for the n, plus 4 times 1700. I'll let you do the math. So that's this yield. And it's also that yield. And then the other one is those enantiomers there. They are 2 times 80. I'm going to call this whole bottom part. Let's call all this like x. 2 times 80 over x. Oh, and I guess I can go times 100 to get my percent, right? All right, and then so that's the total yield for the regiochem of that one. But now if I take this whole thing and I divide it by 2, that's what each of these are. There's an equal amount of those made because they come from that trigonal planar radical that has an equal attack on both sides. And then the challenging one is the final one where you get a bunch of products, right? Now this becomes a stereocenter.
Mark?
Yeah.
Is there a bottom one as well?
I'm doing that one now.
Oh, sorry.
That's okay. I'll just always keep this one the same. I might make you confused if I do that. That's not the way I usually do it. Okay, I'll do it this way. All right, so my bromine can add onto here wedged or dashed. And then it can add onto this one wedged or dashed. And what do I make more of? I make more when the bromine's opposite of the bigger ethyl. So I'm going to say regio-wise, let's make the numbers easy. Let's make this like a 80. Actually, I won't even make it. I'll just say I have more. Won't say the percent of that individually. I'll do this. I'll set up a little side calculation here. Let's go 4 times 1700 all over X from up above here, right? Times 100. Let's call this Y. All right, and I'm going to call this, the percent yield for this one is going to be 0.4 times Y. I don't like having the X in there. It looks like another variable.
Dr. Schmincke,
Yeah.
should that be 80 in terms of the secondary product versus tertiary product? There's the 1700 appears to be for tertiary products.
Oh, you're right. You're right. Thank you for that. Yeah, this is 80.
Thanks, sir.
Thank you. Save me. Okay, so 0.4 Y times 100 will be that one. That's the trans one. And the other one that's trans like that is this one, huh? So I'm taking like 40% of the total and I'm giving it to this guy. And then so that's like 80% for those guys. And then there's 20 left over. So it's like 0.1 Y times 100 for this one. 0.1 Y times 100 for that one. All right, so I got all my percent yields. Now, how are they related? This one, diastereomers. These ones are diastereomers across. Diastereomers. But then here we've got like that stereocenter switch and that one. So they're enantiomers on the diagonal. And I said to give some numbers. So let's say this one's like +7 degrees. That means it's an enantiomer is -7 degrees. And we have the same amount of both, so they're canceling. And if this one's +11 degrees, then this one's -11 degrees. And they're enantiomers, so they're canceling. So my achiral reactant is giving achiral product mixture. All right, I know I went through that one kind of fast, but I have the answer key also on exam key. All right, so let's see. Struggle with Newmans of chairs. Let's do it. Let's do it. So let's see if you can help me make up a nice chair conformation. I'll do it where I give you the cyclohexane chair like flat like this. And let's put some groups on here. So I'll put like a wedge here. What do you want that wedge to be? A methyl, a fluorine, and chlorine, an ethyl, a tert-butyl. Propyl, okay. And I'll make it isopropyl, why not? And then maybe I'll put another one here. I'll make it dashed. And what do you want that to be? Oxobromide, okay. We'll do one more, maybe like here. I'll make it wedge. What's this one gonna be? Alcohol, okay. Let's see now. Okay, so my chairs, I just start off by drawing my framework. And then I go around, add my axials. I like to go axial up, axial down, axial up, axial down, axial up, axial down, then equatorial, out, 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 out. Same with this one, axial up, axial down, axial up, axial down, up, out, out, out. I forgot one. Oh, that was wrong. Down. Equatorials always have to point the opposite direction of your axis. And then I'll number this. I'm going to number it like this. I'm going to go 1, 2, 3, 4, 5, 6. And since 1, 2 are on the left, I'll put my 1, 2 on my chair on the left too. So 1's the most left, so it's still most left. 4 should be most right, still most right. And then my 2's got to go here if I'm doing it the way I like to do it. And then carbon 1 has just hydrogens. Carbon 2 has just hydrogens. Carbon 3 has isopropyl up and a hydrogen down. 4 just hydrogens. 5 bromine down, hydrogen up. 6 got alcohol up, hydrogen there. And then I just transfer those over to this side so I can evaluate these. So 2 is just hydrogens. 3 isopropyl up. Okay, 4 hydrogens. 5 bromine down. 6 OH up. Okay, so what looks to be the more stable chair? This one's a tough one. Because on the left one, we have an axial OH and bromine. They don't want to be axial. But on the right one, we got an axial isopropyl. So the OH and the bromine are kind of small. I'd have to look up the values. I can look it up really quick just to see, to get a guess. Licht. Where am I? Is it? Yeah. So the alcohol costs us to be 0.94 kcals per mole. It costs that much to be axial versus equatorial. And the bromine, it's 0.55. And then the isopropyl, 2.2. So what's bigger? Isopropyl. So this equilibrium is going to lie to the isopropyl equatorial, lower in energy. That one was too close to call. Like I wouldn't just give you this question without the table of data. If I don't give you the table of data, I'll make it more obvious. Like if I had just if I'd switch, say, this alcohol to dashed, then it would have been more obvious that, oh yeah, that big isopropyl is going to dominate. Okay, so, but we didn't do
You're not sharing the
oh, sorry about
thing.
that. Thank you for that. So what I was saying was I could have made this alcohol dashed and that would have changed it to being equatorial with the isopropyl. You probably would have said, oh yeah, 2 are equatorial. That's going to beat out when they're both axial. So if I don't give you the table, I'll make it more obvious in this one, but now you know how to use a table too, right? All right, let's do some Newmans. So do you want to do a Newman from the backside, make it tricky? Let's do it. Let's do a Newman from back here. From 2 to 1. And then if I'm going 2 to 1, oh wow, this one's going to be a hard one. I don't want to do 2 to 1. I want to do 2 to 1. Yeah. Oh no. Maybe I'll do 1 to 6. That's a weird one, huh? Let's do 1 to 6. 2 to 1's got too much in the middle. I try to avoid putting too much in the middle. Let's do 1 to 6. 1 to 6. And then we would do 3 to 4. So this Newman is carbon 1 to 6, carbon 3 to 4. Yep. Okay, so here we go. Draw my owl eyes to start. And I know I'm going 1 to 6, 3 to 4. Now my 1, should carbon 1 be on the right owl eye or the left owl eye?
I have a side question.
Mhm.
If we were to name this, would it be a cyclohexanol?
It would be cyclohexanol, yeah.
Yeah.
So what do you think? Should carbon 1 be on the right alloy or the left? Carbon 1 should be on the right. And carbon 3 should be on the left. You have to imagine you're a person right here with these crazy eyes, right? And then you've got like, I don't know how to draw this very well. You have like your nose pointing this way and your mouth, those are your lips. Here's your neck. Do you see that? Like this would be your right eye, carbon 1 on the right. Okay, and then it's going 1 to 6, huh? So, oh yeah. Now between carbon 1 and 3, this is carbon 1. Oh, sorry. Between carbon 1 and 3, 2 is 2 going up or down? You don't like my avant-garde art or my impressionist art? You call that art? And once I have the first connection, the other ones are easy. And then I'll put all my numbers on here. So I got the 1 to 6. 6 is behind. And then it, as we were discussing, that's 2 in between. 1, 2, 3. So 4 is back here. 5, 6. Yep. All right. So now what's on these carbons? Carbon 1, just hydrogens, easy. Carbon 2, just hydrogens as well. And 1 is axial, pointing straight up. The other one is pointing right at us. So we do it a dot. So dot equals hydrogen coming at you. Okay. And then carbon 3 has isopropyl up, a hydrogen down. Carbon 4, 2 hydrogens, easy. Carbon 5, a bromine down, and a hydrogen pointing away from you. So we draw that as a circle. So the circle equals hydrogen away. And then carbon 6, OH up, hydrogen down. So I think I did it right. The alcohol and the isopropyl are both the same direction. Yeah. And then we draw the chair flip of this. And the chair flip of a Newman, it's pretty easy to do if you just remember that. You draw your owl eyes again. And know in a chair flip, you're going to take like carbon 2 here, which is the head of a chair, is going to get pushed down. So now carbon 2 is going to be down like that. So then I can draw my all staggered conformation. Got them all. Number it again. So it's still going to be 3 right here and 4 right here. And then 1 here and 6 in the back. And then I got 2 between them and 5 in the back still. Okay, let's just go around and put our things on there. Carbon 1, 2 hydrogens. Cake. Carbon 2, 2 hydrogens. 1 hydrogen's pointing down and 1's coming right at you. Carbon 3 has got the isopropyl up. Now it's axial, that's higher energy. Carbon 4, 2 hydrogens. Carbon 5 is a tricky one now. It's going to have a hydrogen up and the bromine coming right at us. So here we have to define it because we can't just put a dot there. That's red as hydrogen. I have to say, oh, this coming right at you is the bromine. 6 is just alcohol up. Equatorial up now. Hydrogen down. There we have it. Alina asked, can you show the mechanism for the first portion? I'm not sure what that's referring to.
I meant if we have to show the bromination mechanism for the alcohol problem.
Oh, I could ask you for that, but if I usually in this syntheses, we don't show the mechanisms. You just go overall reactions and just the major products.
Okay, thank you.
And then James was asking, does the wedge bromine on a ring only react with dashed hydrogens? Are you talking about E2, James? If you are talking about E2, if you have a cyclohexane, the leaving group has to be axial and it only reacts with anti-periplanar, which would be the other axial opposite direction. So why is there no E1 products for tertiary alcohol synthesis? There would be some E1 products. So I just didn't draw the minor products. So for this tertiary alcohol synthesis, your major product is the SN1, but you'd also get some alkenes here and here as minor. Here, I'll draw it in since you asked. But on the exam, you don't have to draw the minor products. It's kind of just a review. So you'll get also and you heated this reaction up instead of cooled it, it would produce more of the E1 and less of the SN1. Isopropyl equator, yeah. Can you do a reaction that has a good nucleophile, but it is hindered? Sure. What about if I did this?
Hey, Mark.
Mhm.
We can't see the screen.
I didn't switch, did I? Thank you. So I react this with, oh, I'm switching it up on you too. I'm drawing the nucleophile on the right, on the left. Okay, what kind of reaction do you expect for this one? I had a question about circle instead of a dot. Oh, shoot. I did this wrong, huh? Thank you for that correction. We go back to panel 4, sorry. This should not be a circle right here. I mean, that should not be a dot right there. That should be a circle. My bad. That circle is a bromine pointing away. Thanks for that correction. Yeah, so this next one, sterically hindered strong nucleophile, it can only do SN2, so it's going to be SN2. So our product would just be the SN2. And then I had a question to do a sigma and pi bonding diagram. We could do that. Let's get it. Let's get it. Sigma and pi. Let's do one with an alkyne, an alkene, and Um, it's going to be a monster. I'll do a ketone in there. And then I'll also throw in my favorite, the allene. Oh. Oop. There we go. Number of my carbons. 1, 2, 3, 4, 5. Oh, I didn't put a tetrahedron in it though, huh? Let me do this. Put a methyl here. Oh, there we go. 1, 2, 3, 4, 5. That's kind of ugly. 5, 5, 6, 7, 8, 9 carbons. Okay. Let me make this a little bit small. And I'm going to do it backwards. I'm going to do the pi bonding diagram first. And this pi bonding diagram is going to be, it's not going to be as big as the sigma. The sigma is going to be huge. So in the pi bonding diagram, remember, you draw all of the atoms. Sigma bonds is just lines. So the first hydrocarbon is tetrahedral. The next one's linear. And it has p orbital perpendicular and in the plane to the sigma bonds. That's bonding. And then also has p orbitals coming in and out of the plane. Wedge dash, right? So that gives it its 2 pi bonds. All right. And then we go to
Is that
carbon.
second green orbital dash back?
Yeah. Oh, that's weird. I did do the dashes. It just didn't take
Oh.
for some reason. Thanks. 1, 2, 3, 4. Five, 6, 7. And again, we've got some p orbitals in and out of the plane here. So those are making that pi bond, and then more in and out of the plane. Okay, and then the tricky part. Let me number my carbons too. Am I not missing anything? 5, 6, 7. Yeah, looking good. Here, beep, beep. And this 7 has a trigonal planar hydrogen there, right? And 7's got, again, p orbitals in and out of the plane to go with this one here on 8. And then 8 has to have another one in the plane to bond with that one. And finally, then that means these hydrogens on the end have to be wedged and dashed. That's the tricky part. Huh? Okay, we got our pi bonding.
How do we know that those the green orbitals are mostly in and out of the page? Is it just for the tetrahedral conformation?
If you have like a trigonal planar atom, then
Mhm.
all 3 of its trigonal planar hybrid orbitals are in the plane.
Mm-hmm.
P orbitals have to be in and out of the plane.
Okay, thank you.
Mhm. All right, so then the sigma we can do now. The sigma is going to be a big long one. Huh? So we'll have the hydrogen here, and then this carbon. We'll do these in blues using its sp3 orbital there. It's got a big one coming out of this. There. These ones always eat up your, oh, I don't want that. Tend to draw these ones so much bigger.
I think maybe the dashes didn't show up again on the.
Oh, I didn't even draw them this
Oh,
time.
you didn't? Okay.
Yeah, I missed it. Thank you. I'm just trying to go through this quickly so I can do other examples too. So 1, 2, 3, 4. We need another one here. One, two, three, 4, and then 5 is coming down. Five's trigonal planar as well. To 6. Just got the oxygen. And this oxygen uses a p orbital. And then 5, 6, and then 7 is trigonal planar as well.
Should we still show the lone pairs on the oxygen, or are you just trying to go quickly?
Yeah, you can, yeah. And then 7. Then my angle changed a little bit, but that's okay. 8, 9. Doop, doop, doop. And then this one's going to be like coming in and out of the plane of the page. I think that's it. Yeah, those sigma ones get huge, huh? All right, so we did sigma pi bonding. Okay, is something SN1 or E1 is the next question I see. So with these, you can have a case where it's only SN1. I don't think you can ever have a case where it's only E1. But they're in competition. Let me show you that case. So only SN1. So why would this one that I'm about to draw be only SN1? Sorry, my iPad crashed. Come on now. I had to restart the jam. All right, here's an example of something that's only SN1. So I'll start off, it'll be a tertiary electrophile. And maybe I'll use like ethanol. It's got to be a weak base. And I'll keep it cool to favor SN1. But this case right here, it'll still have some E1. But if I go 1 carbon away and I eliminate all hydrogens, then it can only be SN1. You need to have hydrogens that are 1 carbon away for E1. And then now why not E2 or why not SN2? SN2 because what? ECA, USE is tertiary. Too crowded. And then, oh, so I didn't really state this as much as I wanted. So no, all carbons that are one carbon away from the leaving group carbon have no hydrogens. No E1 or E2, because it has to have, they both require a hydrogen to be deprotonated, one carbon away. So this one will work if you wanted to just have only and right now I'm just drawing out the overall products from memory, like, because the way I derive that, you know, I'm going to have the bromide as a product, and I'm going to have this protonated ethanol and this product, all this. The reason why I can just do that is because I know the mechanism so well in my head. I can see bromide leaving, carbocation, alcohol adding, another alcohol deprotonating, and there we have it. If you're not to the point where you can just draw the overall products without doing the mechanism, like you don't know the mechanism in your head enough, then you just have to just sit down and practice it. So I would just go to, like, we have lots of examples, right? Like in our animations. If you go to chapter 7, I got a lot of examples in the outline, and then mechanism quiz right here is a good one to do. And then on sheet 2, maybe even better, all these worked out problems, SN1 mechanism and E1 versus reaction point diagram, James's, Ensley's. So if you go to these and each of those mechanisms, you write them out 5 times, say, and keep checking them carefully to make sure you didn't make errors, then you can get to the point where it's in your head, and then everything else is going to make sense. All right, so there's one that goes both, just the SN1, huh? I can't think of an example where I only get E1, but I can do one that gets you both. Let's do an interesting one, maybe like so if I heat this one, what's my major product going to be? Heat's going to favor E1. And when I look at this, I say, okay, carbon with leaving group, one carbon away, no hydrogens, one carbon away, hydrogens. Oh yeah, that's going to be my major product right there, the E1. And then my minor product will be the SN1.
So for E1 and E2 major products, are they both the ones that are lowest in energy?
E1, major energy, lowest energy is the major product, yeah. SN1, not lowest energy. Usually get a racemic mixture.
Well, for E2 though.
For
Like if you
E2,
had
not
several-
not necessarily lowest energy.
Not
Actually,
necessarily.
for E2, we haven't gone over how to determine the lowest energy, but I'll do that in 12B.
Okay.
And then we'll also have, okay, so again, if you can't see this mechanism taking place and just draw out the overall products, yeah, practice. But let me, I'll go ahead and practice with you now too. So I want to make sure you're good at this. So I'll just snap it, put it on the next panel. Talk a little bit about it. So the very first step is just that was ugly. The leaving group leaving, right? So this is a case of a reaction where I have a chiral reactant, but during the mechanism, it makes an achiral intermediate. So even though I started with a chiral reactant, I end with an achiral product mixture. There we go. And now for E1, I got to deprotonate 1 carbon away. So over here, 1 carbon away, I have a hydrogen. Imagine a hinge right here. That's going to make my pi bond. Okay, that's our E1. For SN1, I redraw the carbocation. Always redraw your carbocation. Don't just try to draw more arrows to this one. It gets too cluttered, doesn't look good. We want to have clean mechanisms so we can take them, to the fashion show and be like, look at how beautiful our mechanism is. Go to Milan for the mechanism fashion show. And when this adds, it creates a stereocenter, and it's going to create an equal amount of both enantiomers in this case. And then it doesn't stop there because there's a lot of this solvent T-butanol in this solvolysis. The solvent is reacting. And since there's a lot of this solvent, it can deprotonate it. Even though this equilibrium is like a pK, the equilibrium constant is about 1. There's a lot of solvent. So by the Chatelier's principle, it'll push it towards this product side. Okay. And now why would the heat favor the E1? This one's not as easy to see, actually, because it's a ring. But I think of it as like for E1 to occur, you have to get past, for SN1 to occur, you have to get past these 2 hydrogens. So if your nucleophile is trying to be a nucleophile and it comes trying to squeeze past those, I think when you heat it up, they like jiggle more back and forth. So it's harder to get past and you're more likely to hit them. That's how I go with that one. When it's not a ring, you can see it spinning like the fan analogy we used before. Why don't I just finish this one off? Let's do the reaction coordinate diagram too. Okay, so I'm going to do 2 reaction coordinate diagrams. I'm going to do the SN1 first, or the E1 first, and then the SN1. So I'll just keep them separate to keep it more clear. First step is definitely endothermic because you're just breaking a bond. Oh, I did it again. Shoot. This example is slightly flawed because there's another reaction we haven't learned about yet that's happening, but don't worry about it. I only get 1 product for this E1. Okay, so the first step is definitely endothermic. I wouldn't have to tell you that. The next one's exo and it's overall exo. I'd have to tell you that. And then we add in our activation energy starting from the reactants. This is the activation energy for the rate determining step, the unimolecular rate determining step. There's the next one. Transition state 1, transition state 2. So transition state 1 looks like react products. So this iodide should be far away. And it should be very negative. It's almost fully negative, and the carbocation that's about to form is almost fully formed. And then transition state 2, this one's tricky. It's got a lot going on. One thing people forget on these is the, a lot of times students forget to draw the pi bond forming. So, and it looks like reactants. So this hydrogen that's going to get deprotonated right here is only just starting to break. And this is far away, the alcohol deprotonating there. And this is what people forget, this pi bond that's formed right there, yeah. And then the positive charge is still going to be like plus 3/4 because it's only just starting to lose that positive charge. And then the oxygen is only just starting to get positive. So it's like plus 1/4, looks like the reactants. I want to make that smaller. I wonder if I can. I might not be able to. Oh, I did. Yeah, look at that. I can do it. I can do it. So this is the E1. And I'll do the, I could have done the SN1 on the same one, but I thought I'd make it separate to make it more clear. So it starts off exactly the same. Same rate determining step. Activation energy rate determining step. Transition state 1. All right, in transition state 2, it's going to be exothermic as well. I mean, reaction 2. And I think it's going to be lower than even the starting. Yeah. And then the final product is going to be again exothermic. Remember when transitions, not transition state, but reaction coordinate diagrams were hard for you? Hoping they're easy now. Transition state 1, same as E1 over there. Transition state 2 is going to be different. It's going to look more like reactants. And so this is going to be far away, the oxygen coming on. And the positive charge will only just be starting to decrease. So it'll still be very positive. This is only just starting to form a positive charge, 1/4. And transition state 3. Looks like reactants again. So this will be further away. Charges will be plus 3/4 here. It's still very positive. This one's only like plus 1/4. Oops. Mess up some more room there. There we go. Whew, I think I did it.
Do you also want us to do like 80 for E1 and 24 SN1? Because it's preheating the reaction. Like
If I asked you,
product.
or I usually, for some reason, I don't usually do percents for these. I usually say major, minor, huh?
Okay.
The last request I had was for an E2 reaction. Does that sound good still? Naming of E and Z. So the E2 reaction. You need a strong base. Sterically hindered is best. The electrophile needs a carbon, a 1 carbon away carbon with a hydrogen. So it can be primary, secondary. And then the reactive conformation. Anti-periplanar. Okay, so let's do, I got a cool example for this one. I like this one. I should put this one on the exam. I put these kind of questions on exams before. I like these ones. Let's go where I have a leaving group, say like a bromide. And then over here, I have a hydrogen. And then also a deuterium. Maybe methyl. And then on this side, I'll go methyl as well. Okay, I'll just do that. So I said I wanted a sterically hindered strong base is best. So we'll bring in the E2 superstar. The potassium T butoxide. T butanol. That's sterically hindered with these tert-butyl group and strong base, O minus. Okay, so now this guy, I've got a carbon with a leaving group here. And then next door to that carbon, 1 carbon away, I've got this methyl. It has hydrogens. It can be deprotonated. And this one too has hydrogens. It can be deprotonated as well. So I'm going to get lots of products with this. I'm going to get a product on this side, an alkene. And then I'm gonna also get a product when this is deprotonated or this. Because remember, deuterium is just H2, right? Another hydrogen. So boop, 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 boop. I'll do the easy one first. So this is the, and I'm going to keep these separate. This is my overall reaction. Ugh. And here's my mechanism down here. Okay, so let's do the mechanism first. So I don't really have to worry about the anti-periplanar nature of this hydrogen over here on the methyl because it's it's got 3 hydrogens here, so it's going to give me all the different products. And there's only one really. So here we go. The strong base does not wait around for carbocation. It just goes and attacks right away. So it breaks that. It deprotonates this hydrogen 1 carbon away, making the pi bond there, and then the bromide leaves, all in the same step. 2 molecules in this step. This is the rate determining step, bimolecular rate determining step. What do I get? I get alkene right here. The rest of this stays the same. Okay, got the one product. That's one product we're gonna get. Okay, the other ones will be I'll do next. Which one do you want me to show next? Do you want me to deprotonate the hydrogen or the deuterium next? Okay, I saw hydrogen suggested first. So I'm going to draw it exactly how it is above just to make sure we see the rotation of it. And then I'm going to rotate it to the reactive anti-periplanar conformation. So right now, this hydrogen is actually syn periplanar. It's not on the right position. All right, so it's not react, but I can rotate around this bond and create the same molecule in which that hydrogen is anti-periplanar. And when I do that, my deuterium that was wedged will become dashed, and my methyl that was dashed will become wedged. I can check to make sure I didn't make a mistake with this rotation by doing an RNS calculation. So this one's going to be R, and this will still be R. It should be A, B, C. Yep, it's still R. It's kind of a tough one because the D's in the plane of the page, but it's the same. I'll put that over here maybe. Okay, so there we go. And now I just draw my base, come in here, and deprotonate this anti-periplanar hydrogen. Got a hinge right there. Go pi bond, leaving group leaves. And our product will look like this. If I put the methyl here, the methyl on the left is wedge, on the right it's wedge. Yeah, that's the product I'll get. Put too many lone pairs there. There we go. Okay, so I got the, which alkene did I get? Did I get the E or the Z alkene? Well, on the right side, the methyl is the higher priority. It's higher priority than the deuterium. Over here, I've got a hydrogen and a methyl. Again, the methyl is a higher priority. So this is the Z alkene. So the product in which the deuterium stays on is Z. Let's look at when the deuterium gets deprotonated. I wonder if I can do this one. Shrink it. Can we do it? Can we do it? We can do it, can't we? Yes. Oh, there we go. All right, so now let's rotate it to put the D, the deuterium anti-periplanar. So if I put the deuterium here, what happens to the other two? That would make the hydrogen wedge and the methyl dashed. Let me double check. It should still be R. A, B, C. Yep, still R. Looks good. Okay, we can do this. I'm moving over a bit. Oh, I lost stuff. Strong base, not waiting around. Leaving groups to leave, just goes and deprotonates, right? Or in this case, it's dedeutrating. Deuterating. And what do we look like? We got an alkene with a methyl here. Oh, and this is the trans one, huh? And this product is higher priority here, higher priority, it's trans, because it's only disubtrans, but you can also call it the E alkene. It's a nice one, huh? Oh yeah, deuterobutatoxide, thank you. Deuterium there. Dude. Yes. Okay, let's see, where are we at? Will there be exam leaks today? I don't have exact questions, but if you go through my lecture outlines, it's pretty straightforward, similar to those. And then, so how would we know to deprotonate the deuterium? So what if I'd written this question up like this instead? Would then it look like, oh yeah, we'll deprotonate that hydrogen? Because remember, isotopes of atoms, they pretty much have the exact same reactivity. There is, and it's funny that you mentioned deuterium and H1 isotope, because the deuterium does react slightly different than hydrogen, and we use that to like study reaction mechanisms. But it only reacts, the deuterium reacts a little slower, but it's like slower by a rate of like less than 10%, like, so it's not that big a deal. But other isotopes like carbon 12, carbon 13, they all react pretty much exactly the same. Deuterium, it's slightly different because deuterium's double the mass about, because it has that neutron which weighs the same as the proton about. The neutron's a little heavier. Yeah, so you treat deuteriums just like hydrogens. And using deuteriums is a great way to study a mechanism, because if you're wondering like, oh, what's going to be deprotonated, you put a deuterium there and you see it leave, you're like, oh, I got rid of it. And also a great way to study mechanisms is use like carbon 14 labeled carbons. Like if this one carbon's a carbon 14, you could follow it because it's radioactive. It's really common in biochem where you like feed a dog a glucose molecule where one of the carbons is carbon 14, and then you look in its poop and pee and you find out where that carbon 14 went, and then you start to understand the biological pathways in the body. Okay, so coming down to the wire. Should we do any more of these? So we did a sigma pi, we did a chair, we did Newmans of cyclohexanes. We didn't do Fisher or absolute stereochem. Let's do one more. What would you like? Dealer's choice, or I'm the dealer maybe. Player's choice. Fisher. Sure, we can do Fisher. So aldehydes are common for Fisher projections. I'll do an aldehyde, because there's a lot of important sugars that are aldehydes. Okay, so then I'll maybe put OH here, H here, put a bromine here, H here, OH, F. Okay, so I'm gonna go from the Fisher to the zigzag, ziggity zaggity. So let's go number the carbons first. Oh my goodness. Let me zoom. 1, 2, 3, 4, 5, 6 carbons I did this time. So my zigzag, I'll put the aldehyde on the left. Could have been on the right too, it doesn't matter that much. And I'm going like this, 1, 2, 3, 4, 5, 6. And 6 is easy. It doesn't have any stereochem, so I can just draw that alcohol in. 5 is a little bit tricky. It's a stereocenter. 4, 3, 2. And the way I do these is I just try to visualize that top carbon, carbon number 2. So for me, the OH is wedged out at me. Remember, Fisher's, all the horizontal things are wedged out at you. Wedged out, wedged out, wedged out, wedged out. All right. So the OH is wedged out at me. It's my thumb. And if it's up here and I go like this, like I did, it should be wedged out. OH should be here. And the H should be back. Let me double check that. Yeah, I can visually see that first one. Yeah. And I can check it with absolute configuration. So this is A, B, C, this is S, and this one's going to be A. Oh, I got to remember there's a bromine on the carbon 3. A, B, C. Yeah, this is S too. I'm looking good. So once I got the first one and I'm feeling good about it, which I feel pretty good about it, then I will realize that when you have to like go from the Fisher to the zigzag, every other atom is like twisted the other direction. So my OH on 2 and the bromine on 3 are on opposite sides, but in the zigzag, they'll be on the same side. So now that tells me, oh, bromine's going to be wedged as well. So you see the carbon 2 alcohol is on opposite sides of the bromine in the Fisher. Now they're on the same side. On the zigzag. Okay, so then I just do that same thing. The bromine is on opposite sides of this alcohol in 4. So now in the zigzag, they'll be on the same side. So I put that alcohol there. And then alcohol 4, it's on the same side as fluorine. So now it's going to be opposite sides. And if I want to check, I can do the RNS again. So it's going to be same. A, B, this is going to be R. I should have blue again. R, and this one's going to be A, B, C, R again. Looks good. The next one's going to be A, B, C, R as well. And then this one's A, B, C, R as well. This one is A, B, C, R, and this one is A, R. Looks good. I like it. Want me to do a Fisher going from zigzag to Fisher? Okay, I'll do something different. I'll do like a ketone here. We'll go, I'll put it on this side. Make it a short one. All right, there we go. Number my carbons. And then I'll put the ketone on top. One, 2, 3, 4. Do I have 3 stereostomes? Oh, I didn't number my carbons right. 1, 2, 3, 4, 5. And 5 here just has, oh, what am I doing? 5 here just has an alcohol off of it. No stereochem for that one. 4, okay, 3 has got a stereocenter. So I got to imagine that 3, the alcohol is wedged out at me right now in this zigzag. When I bring it up like this, it's going to be on the right. And let me double check R and S, huh? Let's go A, B, oh, A, B, C. This is R. A, B, C, R. Yeah, looks good. And then since my alcohol on carbon 3 is on the same side as carbon 4, when it has to like flip around to be in this fissure, if they're on the same side in one, they're on the opposite side on the other. So there we go. And then let's do R and S again. A, B, C, this is S. A, B, C, S. Yeah, looks good. Hey. I did those kind of quick. Hopefully you're following it. Sometimes it's actually good to see them quick. I don't know.